Have you ever wondered how Earth's interior works? How does our planet generate heat, produce new crust, and recycle old crust? And what does this have to do with the history of life on Earth? Well, you're in luck, because a new study published in Nature Geoscience has shed some light on these questions by revealing the links between large igneous provinces and subducted iron formations. And you're probably asking, what are large igneous provinces, and maybe what are iron formations? Well, don't worry, I'll explain everything in this episode. But before we get started, let me welcome you to this podcast where we explore the latest discoveries and innovations in geoscience. I'm your host, MrEarthGuy, and today we're going to talk about a fascinating connection between ancient rocks and modern volcanoes. So sit back and relax because this episode's going to be interesting. You're listening to Earth SciShow. Large igneous provinces, or LIPs for short, are massive volcanic eruptions that cover huge areas of land or ocean floor with basaltic lava. They are rare events that occur every few hundred million years, but when they do, they have huge impact on Earth's climate, biosphere, and geodynamics. Some examples of LIPs are the Siberian Traps, which erupted about 250 million years ago and may have caused the largest mass extinction in Earth's history. We have the Deccan Traps, which erupted about 65 million years ago, and these may have contributed to the demise of the dinosaurs along with the giant asteroid that hit the Earth back then. And lastly, we have the Columbia River Basaltic Group. This erupted around 17 million years ago and covered most of the Pacific Northwest with lava. A large igneous province is an extensive mantle melting event. It contributes to the chemical differentiation and lithospheric changes over time. These LIPs have occurred across every continent on Earth, and they're like landscaping events, essentially changing the entire landscape for all living things. However, importantly, they also change the atmospheric composition, which is why you get such large mass extinctions occurring around these intervals. But what causes these eruptions? What triggers such large-scale mantle melting? Well, that's where iron formations come in. Iron formations are a type of sedimentary rock that is rich in iron oxides such as hematite and magnetite. They form in Earth's early oceans between 3.2 to 1 billion years ago, when the atmosphere was mostly devoid of oxygen and the oceans were rich in dissolved iron. Iron formations are unique among sedimentary rocks because they are very dense, up to 40% iron by weight. They are also very distinctive in appearance, often showing alternating bands of red and black colors. Some iron formations are preserved on continents where they can form major ore deposits, but many iron formations have been subducted into the mantle along with the oceanic crust that they were once deposited on. The deposition of iron occurred through an interplay of various chemical and biological processes, resulting in distinct bands of iron-rich sediments. And due to the involvement of biological processes in iron formation, these can provide us clues about the Earth's atmosphere and ocean chemistry during that time. They also play a vital role in understanding the evolution of early life as they contain evidence of ancient microbial activity. Now, I mentioned before that iron formations may have been subducted into the mantle. But what is subduction? Well, subduction is the process by which one tectonic plate sinks beneath another at a convergent boundary. It's how Earth recycles its crust into the mantle, where it can be remelted and reformed into new crust. But what happens to subducted iron formations in the mantle? How do they affect mantle dynamics and heat flow? And how do they relate to the LIPs, or the large igneous provinces? Well, that's what a brand new study in Nature Geoscience is trying to tackle. The scientists wanted to see if there was a correlation between iron formations being deposited into the mantle and the occurrence of LIPs, or large igneous provinces. And by using some statistical analysis of time series data, they showed that from 3.2 to 1 billion years ago, most iron formation deposit ages are correlated with these large igneous provinces, which occurred around 251 million years later. Now that's a pretty long lag, but it makes sense when you consider how long it takes for subducted material to travel through the mantle and reach the core mantle boundary, or the CMB for short. The CMB is the boundary between Earth's solid silicate mantle and the iron-rich nickel core. It's about 2,900 kilometers deep, or about halfway to Earth's center. It's also where some of the most interesting and mysterious phenomena in Earth's interior occur. For example, at the CMB, there are regions called ultra-low velocity zones, or ULVs. These are patches of material that have very low seismic wave speeds compared to their surroundings. They also have higher densities and electrical conductivities. And ULVs are thought to be composed of iron-rich material that has accumulated at the base of the mantle over time. Some of this material may have come from subducted iron formations that have sunk all the way down to the CMB due to the high density. And more importantly, ULVs are also often located near the bases of mantle plumes, which are hot upwellings of material that rise from the deep within the mantle and reach the surface as large igneous provinces or hotspots. And just for some context, hotspots are volcanic eruptions that occur at the surface which aren't at plate boundaries. The velocity and buoyancy of the magma is so strong that it pierces through the crust. One example is the Hawaiian Island chain, which is over 1,500 kilometers long, going from the northwest Pacific plate all the way down to the southeast. These mantle plumes are driven by thermal buoyancy, meaning that they rise because they are hotter than their surroundings. But what makes them so hot, and what determines where they form? One possible answer is that ULVs play a role in plume formation by enhancing heat flow from Earth's core into the lowermost mantle. This could create thermal anomalies that trigger plume upwellings above the ULVs. But how could ULVs enhance heat flow from Earth's core? Well, remember that ULVs are highly conductive due to their iron-rich composition. This means that they can transfer heat more efficiently than normal mantle material by conduction. Conduction is one way that heat can move from one place to another without any physical movement of material. It happens when molecules vibrate faster at higher temperatures and transfer some of their energy to neighboring molecules at lower temperatures. You can think of ULVs as hot plates that sit on top of Earth's core and warm up the overlying mantle by conduction. This could create a temperature difference between regions within the ULVs and regions outside of them, which could drive convection currents in the lower mantle. You can think of convection as a cycle of rising and sinking currents that transport heat from hotter regions to cooler regions. This is how heat moves from most of Earth's mantle. So if ULVs create temperature differences in the lowermost mantle by conduction, they could also create convection currents by buoyancy. These convection currents could then lift up some of the hot material above ULVs into plume heads that rise all the way up to the Earth's surface as large igneous provinces. This is one possible mechanism by which subducted iron formations could influence large igneous province activity by creating highly conducted ULVs at the CMB that facilitate plume formation. There could be other mechanisms as well. For example, subducted iron formations could also affect plume formation by changing the chemical composition or viscosity of the lowermost mantle. These effects are harder to quantify, but could also be important for understanding how Earth's interior works. The bottom line is that subducted iron formations could have profound and previously unrecognized impacts on Earth's evolution by linking Earth's ocean chemistry to the pace of heat flow, crustal production, and chemical differentiation. This link could also have implications for other planets that have subduction-style tectonics, along with oceanic iron deposition, such as early Mars or some exoplanets. These planets could have experienced similar episodes of basaltic crust production, cooling, and outgassing as Earth did, depending on their history of iron formation deposition and subduction. Wow, we've gone through quite a lot this episode, where we've learned how iron formation, which is created both by biological and chemical activity on Earth's surface, may have massive influences for the Earth's history and evolution of the crustal production over time. Iron isn't just a commodity that we use for our technologies, it has a deeper and richer story than previously thought. And whilst there are some anomalies and some clarifications that need further research, it's interesting to know that iron formations travel all the way down to the core mantle boundary and have such large effects on large igneous processes. I hope you enjoyed this episode, and I look forward to sharing more with you soon. Don't forget to hit that follow and subscribe on your podcast platform. You've been listening to Earth SciShow, and I'm your host, MrEarthGuy. And remember, stay curious.